Welcome back to VTSS, and let me welcome Juan, Rubio, Ramirez for his seminar VTSS. Thanks for your time. Thanks also Christian, who agreed to act as an informal discussant. So the rules are very similar to what we usually do. So clarification questions during the presentation. Instead, for more substantial comments, questions, let's just wait until the Q&A after Christian's thoughts. The only change to the rules is we've got less time than usual today, so we'll need to finish at 50 past. So we've asked Juan to just present for some 35 minutes, and then we'll give the floor to Christian. Okay, and neither of you needs to kind of monitor the chat or anything. If people have questions, just unmute, and we'll keep an eye on the chat if it's needed. So Juan, the floor is yours, and thanks for joining us.
Sorry for the time. It's my mess because they invited me to a time and it's England, Europe, and I messed up the train at the time, so I need a little bit shorter time than I thought. But it is what it is. So this paper is with Jonas and Minchul, both at the Philly Fed, and what we try to here is to think about fiscal transfers and whether they are inflationary or not. Okay, that's the main question. Okay. So post-COVID inflation has been well known. I think everyone knows about that. And there has been some discussion about was expansionary fiscal theory, expansionary fiscal policy the cause of it, or it was supply side imbalances. There were some studies talking about that. Okay. We want to try to contribute to that debate, and basically we want to try to use a time-varying SBR. We have some work on that already, some structural time-varying BRs, and I will try to use the machinery to try to answer this question. Okay, we'll see that. Okay, one important thing, okay, to notice on this event is that most of the response that the fiscal response to the pandemic in particular, and we'll talk about also the Great Recession, but let's focus on the pandemic at this moment. So you can see that a big response to the pandemic fiscal response to the pandemic was basically fiscal transfers. So you can see the huge increase on fiscal transfers to GDP around the pandemic, and as I said, there is a little bit of that also in the Great Recession. And on the other side, normally the other measures that we think about consumption or investment or government consumption, investment or GDP, they didn't move that much. So what we're going to try to do here is to think about how the fiscal transfer in particular, not fiscal policy in general, affected inflation during the pandemic. Okay, that's what we're going to try to do here. Okay, just more data on this. You can see that the big gain on the pandemic. You can see the total expenditure GDP that increased the pandemic by 11%, but most of that, almost 7%, was basically due to the transfers to persons. So we're going to focus on that. That's one of. I mean, we are not the first ones to point this out. I just want to mention that. Race with co-authors has pointed out this in a few times before. So we just try to take an empiric side of this issue and try to think about what are the implications for inflation and GDP of this increase on transfers during the pandemic in general, and maybe a little bit more general during the pandemic in particular, and maybe a little bit more general in other periods. Okay, so the tools we want to use here is the rotation invariant time-varying SBR. We have talked about that. That's an idea that comes from Bonanni a few years back, and we have extended a little bit. But the idea basically is going to consider a particular class of time-varying SBRs that allows us to impose identification restrictions. So it moves a little bit away from the statistical identification that most people consider when thinking about time-varying SBRs. So there is all the theory that we have in the paper we just published. So you can look at that and not get into the details. But basically, this is the class of models that we're gonna work in here. And the nice thing about these models is it allows you to separate the inference from identification, because you can use typical sign and zero restrictions to identify the shocks instead of relying on the statistical identification procedures. Okay. Oops. Let me this. Okay. The key is we want to be able to consider rotations like we do in this class of SBRs. We're going to consider rotations of structural parameters, just like we do in constant parameter BRs. But the key now is that we're going to have to consider sequences of rotations, not a single rotation, but sequences of rotations. Okay. And what is the key to this class of SVRs, just to give an introduction to it, is that we're going to consider a prior or law of movement of the structural parameters such that the prior satisfies the rotation invariant feature the same. So basically, it doesn't alter what the likelihood does. And basically, we can map basically everything that we know on constant parameter SVRs will survive for this time variant SVRs if you consider one of these priors here, okay? That basically they are equal across extrusion equivalent sequence of parameters, structural parameters. That's the key, okay? As we do in constant parameters VRs, basically we do the same thing. We map it to a orthogonal reduced form. We have the rotations that allows us to move sequences of structural parameters to sequence of orthogonal reduced form parameters. And we're going to basically do exactly the same that we do in the constant parameter case. That is basically draw from the orthogonal reduced form and map it to a structural wall. Okay, that's the only thing. Okay, one important thing that we do in the theory in the paper is that this class, I mean, we have a theoretical class of structural time variant structural VRs that we can consider with this feature that basically you have this rotation matrix that allows you to travel across observation and equivalent structural parameters. The question is this class of models big or small? So is it something that we can work with or not? And then, okay, we work with the typical mappings that I mentioned between the orthogonal reduced form to the structural parameters. And you can see that there is a mapping, there is a one-to-one mapping, invertible, all the nice features that we normally consider. And what we show is that all the elements of this class can be characterized by any prior that you want in the sequence of reduced forms, plus a uniform prior on the sequence of orthogonal matrices. Okay, and this is key because it will allow us to design algorithms to draw from this class of structural parameters, but also it will allow us to say that basically it's a very large class because any prior that you want to consider on the reduced form, it will work. And then the only thing you have to put on top of it is a uniform prior on the sequences of orthogonal matrices. So it's a very large prior. So the particular, as I say, there is any prior they want to consider on the reduced form will work. We're going to consider a particular prior here. Basically, we call this the random correlation matrices. And the key here is that there is this very nice paper by Archakov and Hansen in Econometric in 2021 that talk about how to reparameterize basically correlation matrices. It's a very nice paper. And we just take advantage of that to think about how to basically draw from the sequence of semi-definite positive matrices that characterize the variance covariance matrix of the reduced form. There is, again, these are all the details are in original paper, and basically we borrow most of the things that we do here is we borrow from Archakov and Hansen, so we don't invent much here. But it's a very nice theory of this mapping between orthogonal matrices, or sorry, correlation matrices and the set of real numbers that makes all the work very simple. So you guys can look into that. That's how the mapping works. Basically, this allows us to go from the structural parameterizations to the right to the reduced forms in the middle, and then you have this delta and this gamma that characterize the correlation matrix. So sorry, the covariance matrices, where yes, the delta is the takes into account of the standard deviations, and the gamma takes into account of the correlation matrices. And as I said, all this is in Archakov Hansen. You can see it, but you don't need to work with this prior you don't want. You can or this prior in the reduced form. You can work with any prior. You can work with Monani's prior. You can work with George's prior if you want. I mean, George's prior has the problem that is order dependent, so you have to think about which of the orders you want to use in the reduced form. But you can work with any prior that you want. The fact that we use this prior in particular, is because it is order invariant, and we have another paper that we show that is empirically relevant. So actually in auto-sample forecast that much better than the other prior that we have considered. So that's why we stick to this prior. There is nothing too deep about this. Okay, and then is the law of motion of the parameters. The autocorrelation matrix is the B. The delta, as I say, is the variance of the reduced form shocks, and the gamma will be the correlations. And we have to define some initial distributions for these parameters, and that's it. That's the typical thing that we do. Nothing we do. Nothing very different. Okay. As always here in these cases is we want to sample from the posterior. So we have this posterior here. So basically the joint posterior of the sequence of total parameters and the parameters that characterize the law of motion of the parameters that I mentioned, the priors. So that's what we want to draw from there, and condition the data and the sign restrictions. Okay. And because these mappings are one-to-one and onto, so we can do all these things, and we can always think about drawing from this posterior as drawing from the reduced form, okay? And then map the reduced form draws into the total parameters. So basically, as I said before, I'm going to repeat this a few times because that's the nice part of the thing that we do. Everything we have learned on the constant parameter models, basically we can exploit it here, but take into account sequences. That's going to make things a little bit more cumbersome and a little bit more time consuming, but basically everything that we learn on the constant parameter case can be exploited in this time variant framework that we describe here. Okay, and basically what we're gonna do in order to draw from this on these posteriors. Oops, I keep letting people in. I assume that's okay, no, Michele, but okay. Basically, we're going to design a Gibbs sampler, basically giving an initial draw of the delta, gamma, and the Qs. We're gonna draw from the B's, conditional on the other typical thing, and the sign restrictions here, and the Q the same thing, and then we have the delta, the gamma, and everything. So basically, we're gonna consider a Gibbs sampler there. Okay. Nothing new there. Nothing. Okay. So the fundamental insight of the Gibbs sampler is that you have to condition on the sign restriction in every step. Okay, that's very important because you want to draw from the joint distribution of these parameters, and then you separate it in conditionals. You have to condition every single step. In every single step, you have to draw from taking into account the sign restrictions. Okay, and that's going to be the part that is you have to be careful with. In the case of the B or the beta, sorry, it's kind of simple because that's a normal distribution. So basically, you have these sign restrictions there, and basically that sign restriction is truncated normal. So it basically defines the truncated normal of the B given delta, gamma, and Q. So that's kind of easy to do. Okay. In the case of the Q, it's exactly the same. Given the beta sigma Q, you're going to have a truncated uniform because you can use an accept reject algorithm to do step 3. Basically, the same thing. Okay, it's a little bit harder to draw from the delta and the gamma. Okay, because they don't have a standard distribution, so it's a little bit harder, and they are huge because you have these sequences. So basically, we use an elliptical sampler there. I don't want to go into details about this. So if someone is interested in how these algorithms work, they can send me an email and talk about it. But that's a little bit what it makes a little bit harder the Gibbs sampler because you have to use elliptical sampler to draw the jointly the delta and the gamma. And then we basically do a standard hyperparameter updating that is not very demanding. Okay, that's very thing. Importantly, okay, this is basically the algorithm that we describe in the review economic studies, but here we want to do a little twist to the algorithm. We want to consider we're going to consider zero restrictions. So we want to include zero restrictions in some identification, and that complicates things quite a bit. Okay, because now basically you want to have to be drawing the same. So basically you go back to the algorithm that we have here. The nice thing about these manifolds that are implied by these restrictions is that they are open sets in the set that the posterior distribution lives in. So it's not very complicated to draw from these open sets because they don't reduce, these manifolds don't reduce the dimension. But once you impose zero restrictions, you have a problem of reducing the dimension. The manifold reducing the constraint basically reduces the dimension of the posterior, and that becomes in general quite hard. Okay, but there is a few cases where it's not hard, and that's the one to take advantage of here. So basically, you want to restrict just one particular shock. So you only want to restrict with zeros one particular shock. You can basically show that you can order the variables and the restrictions without loss of generality because it doesn't matter the order, as I said at the beginning in this model, but you can order the variables and the restrictions in such a way that you are only restricted C entries of the first column of the A, for example, of L0. Doesn't matter you want to do the A or the L0 because that doesn't matter. You can do the, and that basically is just imposing restriction in the first column, in the first column of A, and we can show that from the conditional distribution that we showed before. Actually, go back to here from the 2, the 3, the 4, and the 5. The only one that gets restricted is 3. So that zero restriction will not condition beta, will not condition delta and gamma, and will not condition the hyperparameters. So the only thing we have to do is to condition the Q on those zero restrictions. Just in the case that you want to restrict a single column of L0 or A0, not both, but just one of them. You can do that. The only thing you can just show that the zero restriction appears only in this step of the Gibbs sampler. Actually, and we have some nice techniques to draw from restricted Qs. So that's not from the set of conditional distribution that we have here. That's the one that is the simplest to draw condition on the zeros, and we know how to do that. And then basically we use these algorithms to do that. So the message here is that we can impose some zero restrictions on the first column of either A or L0. Okay, in this case, particular case we're going to do here is going to be A, but you could do it also in L0 because we're gonna put some restriction on the monetary policy, but you will see.
So Rubio, can I ask a question?
Yeah.
So do I understand correctly that the trick here is that the order doesn't matter because I have the extra sign restrictions. So suppose I only wanted to do zero restrictions, then it would not be enough to assure that the order of the other shock doesn't matter. So the order doesn't matter. If I have all sign restriction in your other paper, you show that the order doesn't matter. But in this case, and if you add that as zero, then it still doesn't matter, or is
let me say, I think, okay, let me say. So what happens is that this particular prior, we call the random coefficient prior, the order of the variables does not matter. Okay, so you can always reorder so you reorder the variables. There is the prior gets ordered in the same way, and doesn't matter. Doesn't matter which order you put the variables in. There is always you can always reparameterize the prior to get exactly the same prior. There is no problem with that. Okay, that's one point. For example, you compare it with Giorgio's prior. That's not the case. Giorgio's prior, you have an ordering, and then you want to use the same model, and you change the order of the variables. There is no another prior that allows you to draw from that. So you can, the order of the variables matter. So there is an interaction between the order and the prior. That's what happened with Giorgio. So in this only reduced form, our reduced form prior allows you to order the variables. It doesn't matter how you order them. Okay, good. Now let's say that you want to introduce zero restrictions. Okay, our algorithm to introduce restrictions only allows me to put zeros on the first C, let's call it Z, we call it Z, C entries of A or L0, doesn't matter, A0 or L0. So if I put the zero restrictions on the first, let's say 3, imagine I want to put 3 zeros, okay? An algorithm says that you have to order the variables such that the zeros are the first 3 entries. Let's say that the zeros are in A0. So the zeros has to be in entry 1, entry 2, and entry 3 of A0, of A, sorry. That's what, then I can apply my algorithm. But because my reduced from prior allows me to order the variables the way I want, I can always order the variables such that the 3 zeros I want to put are in the first 3 variables. That's the interaction between the order doesn't matter, and I can introduce zero restrictions.
I could potentially only have the zero restriction in the first column and no sign restrictions?
Yeah, no problem.
Okay, thank you.
Okay. Good. But that's a technicality. Moving out of that makes it complicated because then the zero restrictions enter on the conditional distributions of beta and delta and gamma. And that gets very complicated. I mean, theoretically, you can do it because only volume elements appear. The nice thing is the volume element here is basically a constant. So the volume element, it's a very particular volume element that is a constant, and then you can do it very easily. In the other cases, the volume elements will not be constant, and then basically you can do it theoretically. I can write the conditional distribution with no problem. But in general, that conditional distribution is going to be very, very slow to draw from because I can compute these volume elements. I have to compute these volume elements and the ratios. And because I have sequences, I have to compute millions of volume elements, and it's totally undoable. That's the whole thing. The nice thing about this trick is that allows me to basically forget about volume elements because I can show it's a constant volume element. That's the whole thing. Okay. We're working. Okay, well, we can talk about that if we have time. But okay. Yeah, this is what I said. Basically, this is what I wanted to say. So basically, normally having SPDs, semi-definite positive matrix is kind of hard. So we have this trick of the random coefficient matrix that I mentioned before. But once you put the zeros, it gets much more complicated. So you have to draw from this distribution. Think about it. You have to draw from the sigma condition on the zero restrictions. So fixing a Q, given I have a draw from a Q, I will have to find the sigma. I will be, you see, this basically this describes a manifold. There is a reduction basically is a constraint on the sigma, and then I will have to think about the constraint, how the constraint affects the law of motion of the sigma. And because I write the law of motion in terms of gamma and delta, I don't know how these constraints translate to constraints on gamma and delta. That mapping, I don't know how to construct it in particular. That makes it very hard. But as I said, I can show if I only put restrictions in the first column, and because I use Cholesky, you have to think about Cholesky. Cholesky allows me because there is a lot of zeros there. So basically, this constraint doesn't matter. So basically, drawing from the sigma condition of the constraint and the sigma without the constraint, it doesn't matter. So that's the whole thing here. Okay. So this was the introduction to the methodology, but let's go to a little bit to the economics. Okay. So this is the model specification. So basically consider a model with C variables, and RC means random coefficient. That basically describes the project that we have, the reduced form project that we use. Okay, and then we have transfer GDP, output, GDP deflator, interest rates, some sense of supplier delivery index because we want to say congestion, we want to talk about congestions, and personal savings because you will see, I mean, we tried the model with personal savings and without personal savings, and the results change a little bit because there is a lot of the transfers. So people save some of that thing, and so it's important to have that variable to basically absorb part of the transfer that you get. We run the sample since 1948 Q2 to 2019 Q4 because we run some. We could go after. We can go COVID. I mean, there's no problem with that. But if we want to do some error decomposition exercise, we have to stop and do forecasting at some moment. We do 2019 Q4. Because that's when COVID came, and I want to do that analysis there. When we do if I have time to go over the Great Recession, you will see that we stop the identification just before the Great Recession the same way. We tried to estimate the model until the end of the sample, and there's no problem. You can. The results don't change that much. Even if I do the error decomposition with the whole filtering, with the whole smoothing of the parameters, the results are not very different. But we want to be coherent, so we copy Domenico and Giorgio that have a very nice paper on similar issues, not exactly the same, with similar issues, and we basically copy their strategy. Okay. Okay, so this is the fiscal transfers policy. Actually, I said monetary policy before but I meant fiscal. Sorry, I'm too used to do monetary policy. So this is the policy rule that we have. So basically, we have transfer depends on output, inflation, interest rates, basically all the variables that we have, and we have the shock that we want to identify. Okay, and the restriction that we want to say is that basically GDP only reacts contemporaneously to output. Basically, it forgets a little bit about the others. This is an extreme case. We want to throw the zeros. Actually, if you put bounds, the results are quite similar, but we want to try with basically imposing some kind of behavior there. And then we need, if we want to basically restrict this, we have to basically say that the C, P, and the C, Y, I, D, and PSR have to be zero. That's why we have to put the zeros. Okay, and these are restrictions to the A matrix, because that's the behavior matrix. And what happens here is I say I only put restrictions here, so I can use this trick that I mentioned and go forward and impose the zeros. Okay, very good. So then the other shocks, okay, are going to be identified only with some restrictions. So the only thing I can, as I said before, I can only identify one shock with zeros, but I cannot identify the other shocks with some restrictions. I'm going to impose zeros in the rest. So these are demand, monetary policy, supply, and other supply. So basically, between supply and other supply for us will be a typical supply shock. That's what we want to say a little bit. And other supply will be a bit of congestion. The idea is that basically you congest the delays. Okay. Okay, we use okay, sorry. The first thing we do now is like, okay, do we need a constant parameter BR or not? Do we need a time varying BR or not? So that's the first thing we try to do here. Okay, and then the thing that we do is like we estimate a window of 40 years window of constant parameter BR. Okay, and we look a little bit to the impulse response functions that we get in these parameters. These are the impulse response functions of output, prices, and interest rates to the transfer shock, and you can see that there is quite a bit of time variation. So there is, that's the first thing. Basically, this tells us that we need stochastic volatility. This doesn't tell us that we need parameter drift at this moment, it's total parameter drift, but it basically tells us that we need stochastic volatility. But then to go a little bit further, okay, let's look at the systematic response. This is something. So you have a model with stochastic volatility. It can be shown that the systematic part, okay, once you normalize the equations, basically will be constant, or you can have it will be constant, okay. And you can see here that these things are not constant. Basically, you have this variation, okay? They move period by period, but there is a huge change that happens from 2005 to 2012. So basically related basically to the Great Recession, but there is some change there that will not be able to be handled by a stochastic volatility model, stochastic volatility only model, okay? So it's not only the fact that we want to use these models to separate inference from identification. It's also the fact that the data tells us that we need a model that has a little bit more than stochastic volatility. Okay. So we need to consider a time varying model. So we do that, and this is basically the main message of the paper. Okay, so let's do some historical decomposition of what shocks are behind the movement. So the unexpected movements that we saw in the different variables. I want to focus basically on GDP, real GDP per capita, and the GDP deflator, and try to think about what are the things that are behind these things. Okay. The first thing you can see, there is huge shocks, huge transfer shocks, two of them actually during the pandemic. Remember, there were 2 rounds of checks that basically were sent around, and you can see them. And then let's see what happens to basically GDP and inflation. And you can see that these checks, these surprise checks, not only the check, the surprise checks help basically to sustain GDP dramatically. Without dot checks, GDP will have basically plunged even more. That we saw, because you have these supply forces and demand at the beginning were pulling basically output down, and basically the only thing that kept it alive was the transfer. So in that sense, the transfer were very expansionary on GDP, but at least at the beginning they were a little bit behind the inflation. In the long run, no, actually they were not very long-lived, the effects on inflation. So in the long run was mostly a supply side shock that brought inflation up. And we can talk about which ones were they, the supply chain or the push shock, and you can see that maybe the supply chain shocks, basically congestions, were the ones that were behind the inflation. But mostly what happens here is that there was an increase on inflation at the beginning due to the transfer shocks. There was this trade-off between keeping the GDP alive and the inflation. But in the long run, where the main force behind the inflation that we saw in 2022, 21, 22 was basically the supply side, was not demand. Okay, that's something that is important, and something that actual models tells us is that basically monetary policy was quite restrictive. You can see the pinky thing is monetary policy. Monetary policy was not very expansionary at that moment. Okay, they was very restrictive, quite restrictive. It was trying to pull inflation down. Okay, that's basically the message that we get. This trade-off basically between these transfers can be very useful to push output, but there were some trade-offs because they cost, at least at the beginning, they cost quite a bit of inflation. Okay, that's the main message that we have here. What will happen if we have run a constant parameter BER? So what would mean the conclusion? The conclusion will be a little bit different in the sense that you will see that the effects of these transfers on GDP will have been much larger, and the effects on inflation will be a little bit smaller. So basically, this trade-off I was mentioning before, okay, will not be as strong. Sorry. I was going to sneeze, but no, not anymore. So basically the trade-off I was mentioning before between pushing output and creating inflation, or pushing output in the positive side and creating inflation, will not be as strong. You have estimated a constant parameter BER. Okay. Another thing important to notice is that the effects of monetary policy will have been pretty different. Basically, we'll say that monetary policy had basically no role in what happened, and basically with the time bar BER, you can see that monetary policy was a little bit restrictive and trying to push inflation down. And you can see the same thing happen in GDP. You don't have this inflationary side of monetary policy on GDP. Okay, that's with time barring. Okay, this is the comparison. I mean, it's every time we presented this, people ask us, how do you do in comparison with Giorgio Primiceri? Basically, Giorgio's and Domenico's point is that inflation was demand side inflation. That's the main conclusion that they have in their paper. Actually, we say that not actually inflation was mostly supply side. The demand side was not very important for inflation. So actually, I have to say something. Domenico there was an MBR conference last week that Juan has presented in, and Domenico was one of the discussions, and I suspect that he focused in this graph. And he made a good point, is that we need to think about if demand had congestion effects or not. So we are not restricting that right now. Basically, we are saying that we are not taking any stand of how demand affected the supply indexes, the delivery supply indexes here. And he showed, because he asked for the codes, we let it him, so there's nothing much to hide. So he played with it a little bit, and he showed that you allow demand to have some kind of congestion effects, basically creating some back orders on the supply side. This resolves quite a bit. So this graph, the top right graph that I showed you, actually the rest is not very different, but this top right graph that I showed to you, it changed quite a bit. So demand takes much more of a role once you consider that demand shocks can have some kind of congestion effect on this delivery index that I mentioned here. So something we're exploring that I wanted to mention, that basically this is the most, like you want. I mean, our paper is not basically what are the causes of inflation, no, in the sense that we take this particular event just to try to understand what are the effects of transfers into inflation, and this particular event is very attractive because you have this huge increase in inflation that you observe, but it's not. We're not taking into account. We're not behind this. We're not behind explaining what happened exactly here. But as a consequence, is this. So we don't want to get into a direct discussion with Giorgio and Domenico, because we mostly lose, I'm sure. But I wanted to point this out. Okay. Very good. Yeah, this is the import response functions a little bit. Okay. So basically, what is the conclusion after looking at the pandemic? Basically, fiscal transfer shock can be inflationary. Okay, but there is an important trade-off between output and prices. Okay, and time bar SBR makes this trade-off stronger. So you do a constant parameter BER, you will not see this strong trade-off between that. So basically, you can get big push on output without losing too much on inflation. That's basically the message. So you need a time bar BER to see this important trade-off. And inflation was basically supply side. That's what we find, and it's very important to actually, that's another thing that when you do it with Giorgio, I don't know, it's not here the graph of Giorgio, but Giorgio says basically demand did not support that much output during the pandemic, but this is because they didn't consider transfers into their BER. Once you put transfer and you identify transfer shocks, we see that transfer were very useful to support output. So that's something that you need to consider. So basically, the message is that you want to think about the trade-off. You need to consider time bar and SBRs, and if you want to think about demand being of a strong support to output, you need to consider transfer shocks. Okay, that's something. Okay. So now let's go to the Great Recession. So one thing that we think, okay, what happens in the Great Recession? What happens if we do exactly the same in the Great Recession? We stop in 2007 Q4, if I remember well. I'm not sure that we stop there, and we do the same analysis. Okay, we do exactly the same exercise, and we do the same analysis. The first thing you notice that the transfer shocks were not that important. Okay, so there were not huge transfer shocks during the pandemic. and therefore output dropped much more. Actually, transfer was, they have a little bit of negative supply shocks during that time, and the behavior of some of the other variables is quite similar. Okay, you have this supply side pushing tremendously inflation up. Okay, you have monetary policy being a little bit restrictive, even more restrictive than it was during the pandemic. And you can see the shocks being much more restrictive. Okay, but the big difference here is that you don't have a huge inflation, at least at the beginning. The inflation is not that big, and your output basically is below potential for a very long time. You see the gap between the forecast and the output, I mean, it stays very wide. It's basically 10%, even more by the end of the forecasting period. And the big difference that you didn't have here, the transfers. So basically, what is missing from this picture is that the transfers were not there. That's the main message there. So you have had a big increase in transfer in 2008 as we had in 2020. Maybe we will not be talking about a great recession right now. Okay. And you can see a little bit of the trade-off here, because we had a great recession, we don't have the great inflation. In some sense, you have to choose. You're going to have the great inflation or the great recession, one of the two. You have to decide what is best. Okay. Yeah, that's what I say. Fiscal transfers, small fiscal transfers. Fiscal transfers didn't need to be inflationary in this case, so actually they are not, and there is no arm trade-off. Okay. So one thing we want to point out, because actually I think these slides are changed. Okay, one thing we wanted to say here. Let me I think forget about the last slide, because I think we changed the order not on purpose. So what I wanted to say here is that, so imagine now, because one of the main differences is that we don't have these transfer shocks in the Great Recession. So what we want to do here is like, let's impose the shocks of the pandemic into the Great Recession. I mean, this is not a good contrafactual, we know about that. I mean, I'm sure Christian is going to kill me with this contrafactual, but it's okay. I hope I can leave for my train before he starts talking. But let's do the exercise of trying to impose these shocks of the pandemic in the Great Recession. Okay, let's see if what will be the effects that will have on inflation. Okay, and actual GDP. So the first thing we notice that because we had these huge shocks, GDP will not have dropped that much. Actually, we have increased a little, okay? Because we have these huge, I mean, the transfer shocks during the pandemic were tremendous. So you have imposed those, you have had that GDP will not have suffered. Indeed, it will have been maybe positive, okay? Importantly, okay, you can see that inflation will have increased a little. Okay, it will have increased from 2 maybe to 3-4%. The red line is basically is the contrafactual. But you can see that it's not as big as you have observed during the pandemic. And the main difference is the systematic part of monetary policy. Okay, as you can see on the right-hand side, the interest rates systematically, because this comes from the transfer shocks, will have increased much more. Okay, even in relative terms to the pandemic. So the systematic, the monetary policy was not as accommodative to this kind of shocks during the pandemic, during the Great Recession that had been during the pandemic. So that is the big difference. Okay, so transfer shocks can be inflationary. Okay, as long as monetary policy is not is accommodative. So you can always use monetary policy to basically clean up some of the effects. We know this from a long time ago. So it's very nice that the model shows up. So you have a systematic part of monetary policy that reacts very strongly to these transfer shocks. You will clean up some of the effects that you have in inflation. So now I can go to this slide. Fiscal transfer shocks do not need to be inflationary. They are going to be inflationary as long as monetary policy is very accommodative, and in this case, the trade-off is not there as we saw before. Okay.
We might need to take it to a close. At least we ensure Christian has got enough time.
Okay. So, but that's it. I said everything that I wanted to say. Stop share.